and our today's speaker, Robert Spicer, and his lecture about palaeoaltimetry. Please, you're welcome to speak.
Thank you. Well, hello everybody, and I see there's some people from China as well as Russia and elsewhere. Today's talk is basically one of palaeoaltimetry, measuring past surface height. And I'm going to look at the ways in which plant fossils and isotopes can be used to do that, preferably in combination. I could alternatively have titled this talk, The Ups and Downs of Palaeoaltimetry, the Case for Consilience, because consilience is a very important concept. It means the agreement or harmony among two or more disparate scholarly disciplines regarding concepts or underlying principles. And unfortunately, in science, we often forget that there are people working on similar problems, but using different techniques when we come to publish our results. And often, we find that the different techniques or as underlying assumptions lead to quite different outcomes. And yet, in fact, I'm reviewing a paper at the moment that looks at a particular aspect of, let's just not identify the people, of science, where they've ignored other evidence that is contrary to their findings. They haven't even discussed it. So this is or can be a big problem, leading to a lot of contradictory information in the literature and a lot of confusion. So I would argue very strongly that we need to attempt consilience in our research. The reason why consilience became important is through the Umbrella Project, which I've spoken about previously. This is a project that involved climate modelers, geologists, isotope geochemists, and paleontologists, trying to look at the evolution of the Tibetan Plateau and surrounding regions. And today, what I want to do is concentrate on the overlaps between climate modeling and isotope geochemistry and paleontology, occupying this sort of zone. We're going to be looking at climate proxies indirectly and directly. These can be translated into paleoelevations. We're going to be looking at isotope fractionation and as that changes as a parcel of air traverses a landscape. And by combining these various things, get a better understanding of the paleo landscape, in particular across the Tibetan region. First of all, I need to explain what I mean by the Tibetan region, sometimes called the Pan-Tibetan region. The Tibetan Plateau is a major feature of the planet today. It's the highest and largest piece of real estate in the sky, and we know from a variety of different studies, both theoretical and modeling, etc., that the Tibetan Plateau has a huge influence on atmospheric circulation over Asia, and in particular the Asian monsoon system. But the Tibetan Plateau is an area that is quite poorly defined. Quite often people include the Hengduan Mountains. By definition, these are not a plateau because they have some of the highest relief in the world, with mountain top to valley bottom ranging over 3 kilometers. So that is not flat by any definition. So Liu et al. 2022 attempted to try and rationalize our nomenclature across this region, separating out the Himalaya from the relatively flat area of the Tibetan Plateau, although it does include mountain systems such as the Gangdesi and the Tangula, from the Hengduan Mountains, which geologically represent an extrusion of the Tibetan Plateau terrains, towards the east, but nevertheless are not a plateau in geomorphological terms. And to the north, we have the mountains of Central Asia. So I'm following the Liu et al. Definitions when I refer to Hengduan Mountains or Himalaya or Tibetan Plateau. Now, the evolution of the Tibetan Plateau and surrounding mountains is controversial to say the least, or our understanding of it has a great deal of diversity within that understanding. Some of you may have seen this slide before. I've used it previously. And back in the 1980s, the geophysicists came up with the idea that the thickened mantle lithosphere beneath Tibet, under the compression between India against Asia, would have thickened the mantle lithosphere. This would have projected down into the hot asthenosphere and eventually fallen away or thermally delaminated, giving rise to a sudden rebound, surface rebound or rise of what they were calling the Tibetan Plateau then, from around 3 kilometers to 5 kilometers, approximately 10 million years ago, when it was assumed back then that there was an intensification of the Asian monsoon. And this all seemed very nice, very tidy. Unfortunately, it generated a lot of debate or fortunately actually, generated a lot of debate with the geologists, complaining that this very simplistic Pleistocene type model did not incorporate all of the complex geology that we knew existed within the Tibetan region. And consequently, in 2001, Toponier et al. Suggested that actually Tibet grew progressively from the southwest towards the northeast over time. So we have an Eocene elevation of Tibet, an Oligocene elevation of Tibet, and a Quaternary evolution of Tibet up in the northeast. What they didn't do was really differentiate the Himalaya from the rest of the plateau, and there is a major suture here, the Yarlong Sangpo suture, that separates the Indian plate from the Eurasian plate. But in the Toponier et al. Paper, this is very ambiguous, and they seem to imply that the Himalaya rose at the same time as the Eocene Tibet. In 2006, new palaeoaltimetry results were published by Rowley and Curry in Nature, and in a commentary, Mulch and Chamberlain produced this diagram, again following on from Toponier, suggesting a progressive uplift of Tibet from the southwest towards the northeast over time, and again not differentiating the Himalaya from the rest of the plateau region. And here you can see in modern topography the Yarlong Sangpo suture, which is totally ignored in this map. There's been a lot of controversy over the years, and basically it's now boiled down to two competing end-member growth models. So we have a model here where there is a high proto-Tibetan plateau in the Eocene, and that this proto-Tibetan plateau grew southwards to form the Himalaya in the Neogene, and also northwards, so that the whole of the modern plateau system was developed by the end of the Neogene. Contrasting to that is the idea that we have the high Gangdesi Mountains that I mentioned earlier, north of which is the Changtang Mountains or Tanggula Mountains, and between them in the Paleogene, and including most of the Eocene, we have a wide, deep valley. So the competition is between a very high, more than 4 kilometer proto-Tibetan plateau in the Eocene versus a low valley in the Eocene. So I'm just going to take those two end-member models and explore how we might measure palaeoaltimetry, particularly in central Tibet, over time, and see if we can find any consilience amongst the different methodologies. Well, first of all, what are the different methodologies? Measuring past surface height is absolutely crucial to understanding links between orography, monsoon dynamics, and biodiversity, particularly if you want to give a climate model a realistic topography to generate atmospheric circulation and monsoon parameters that you can go back and compare with the geological proxies. So we need to be able to measure past surface heights. There are a number of ways in which we can do that. The main ones are by thermal lapse rates. Basically, the higher you go, the colder it gets. Conservation of energy principles and stable isotope fractionation. And I'm going to go through these three main methodologies one by one, starting with thermal lapse rates. Now, plants, we all know, are rather good at recording climate. Most of us have been involved in that sort of activity from time to time. And when we're using plants, we can use nearest living relative techniques, such as coexistence approach or various other variants on that. Or we can use leaf form, i.e. leaf physiognomy or clamp-based approaches. These will give you an estimate, a quantitative estimate of past temperature, and using that temperature, one way or another, it has been assumed over time that we can translate the temperature changes that we get into changes in surface height. We can also measure temperature using things called clumped isotopes, and I'll come on to that in a minute. And also carbon isotope fractionation during carbon fixation, i.e. during photosynthesis. These are all methods which can be related to thermal lapse rates. And again, I will talk a little bit more about this as we go through. So, thermal lapse rates. This diagram here, going back to the 1890s, shows altitudinal zones on a mountain in Arizona, and you can see that we go from desert down at the bottom to alpine tundra on the top of the mountain, and this represents a progressive drop in temperature as we go upwards. Notice also in this diagram that the altitudinal vegetation zones differ depending on aspect. So on a south-facing slope, the zones tend to be higher on the mountain than on the north-facing slope. Of course, the reverse would be true in the southern hemisphere, where the north-facing slope would be the warmer slope. We can measure thermal lapse rates in the free air. This is quite often called the environmental lapse rate. And this is simply the temperature change with elevation in a column of non-convecting air away from any land surface. This is all very well and has been applied in the past to paleobotanical data. Axelrod used to use this global mean average in some of his work. And he also used what is called a terrestrial lapse rate. Now, the terrestrial lapse rate is somewhat different because it measures elevation or measures temperature change with elevation on the land surface where our geological proxies are formed, whether they be isotopes in carbonates or whether they be in leaf form or as changes in taxonomic composition, for example. This terrestrial lapse rate, the modern day global average is 5.5 degrees Celsius per kilometre, is somewhat lower than the global mean free air lapse rate or environmental lapse rate, which is 6.5. And this is because the land surface heats up more than free air does, so you get a lower a smaller reduction in temperature with elevation on the land surface than you do in a column of free air. As I said, we need to really focus on the terrestrial lapse rate when we're dealing with geological proxies. The problem with the terrestrial thermal lapse rate is that it's highly variable in space and time. So you can see here in this diagram, here is an annual terrestrial thermal lapse rate derived from ERA data. This is observational data. And you can see that in the tropics here over Central Africa, we've got values that run into 6 or 7. But if we go to Antarctica, there are values which are practically 0. So, and over Greenland, for example, we've got very low terrestrial lapse rates, but at a similar latitude in northern Russia, we have much higher lapse rates. So you can't just say it's latitudinally dependent. Also, it varies, the thermal lapse rate varies from season to season. So here we've got the summer, northern summer versus the northern winter, and you can see the spatial variation is quite different even to the mean annual. So this means that your terrestrial thermal lapse rates derived from whatever proxy depends on when the proxy is being formed or what seasonal signature the proxy is capturing. Terrestrial thermal lapse rate also varies with atmospheric composition, so it changes over geological timescales as the nature of the atmosphere changes. During our umbrella project, we decided to test whether in a model environment the terrestrial thermal lapse rates were reliable indicators of elevation. So here you can see all these black symbols here. These are annual terrestrial thermal lapse rates, and the different colors represent different seasons, with green representing spring. Now, this diagram may not be familiar to many of you, but basically in simple terms, the closer we are to this red star, the better the skill of our methodology. So you can see that using annual terrestrial thermal lapse rates show extremely poor skill at reconstructing a landscape within the model. The only ones that come close are spring terrestrial thermal lapse rates, but even these show a high degree of scatter based on different scenarios compared to where we want to be, which is at the red star. Now, these terrestrial thermal lapse rates all use the conventional dry bulb thermometer, the kind of thermometer that you would use in your house or garden or laboratory, where there is a dry bulb and you're measuring temperature that way. But in meteorology, we can also use a wet bulb thermometer where we immerse the bottom of the thermometer in a moist environment, typically a moist wick, and evaporation from that surface will reduce the temperature. And this temperature is called the wet bulb temperature. Now, when we do the same experiment using wet bulb temperatures, you can see that it doesn't matter when in the year we use our wet bulb terrestrial thermal lapse rate, we get much, much better skill at reproducing the landscape within the model. So basically, wet bulb terrestrial thermal lapse rates are the way to go, not dry bulb. And this is because the wet bulb incorporates changes in moisture that are associated with changes in elevation. So what does this mean? It means that almost all thermal lapse rate palaeoaltimetry in the literature to date, whether you use pollen, leaves, clumped isotopes, or whatever, they've all used dry bulb temperatures. They've all been calibrated against dry bulb temperatures, and so all are unreliable. Basically, you can throw those all in the bin. You still get numbers using dry bulb, but what those dry bulb thermal lapse rates give you in terms of an elevation is anybody's guess. Now, we can measure wet bulb temperatures in the past Particularly, I've been interested in developing clamp, as you know, over the years, and it turns out leaves are extremely good predictors of wet bulb mean annual temperatures. Unsurprising, because plants, as I've said previously and many times, plants are interested in both temperature and moisture, and so tend to code for both, and both are incorporated in wet bulb temperatures. So here is our clamp regression, and we can get wet bulb temperatures from the past using clamp. Another method that uses clamp is the conservation of energy. I won't spend a lot of time on this. Most of you are familiar with this by now. This is based on the principle that moist static energy is conserved in a parcel of air as that air rises up and over a mountain system. Moist static energy, again, is a function of temperature and moisture, and because it is conserved, and moist static energy is the product of both enthalpy, moist enthalpy, and potential energy, as you go up a slope, the potential energy increases and moist enthalpy decreases in order to keep moist static energy the same. This means that if you measure moist static energy at two elevations, low and high, and divide them by the acceleration due to gravity, which is one component, when you multiply acceleration due to gravity by height, you get potential energy. When you divide by this constant g, you get the height difference between your two moist enthalpy measurements. And this is particularly powerful because when we test this in a model scenario, and here we've got Southeast Asia, we've got the Tibetan region represented in this model by a plateau, this model with a valley in between, and this version here is a very high modern plateau. Moist static energy, or rather using moist enthalpy in the way that I've just described, is capable of reproducing these model landscapes extremely well and resolves the Central Valley even in this scenario too. So we've got great confidence in that approach, and again, leaves are extremely good at providing you with an estimate of ancient, or fossil leaves are, of ancient moist enthalpy. Here is the clamp regression. We're now moving on to palaeoaltimetry using stable isotope fractionation. This is a very popular method. It's a favorite of many geologists. Geologists seem to be inherently suspicious of anything green, i.e. leaves, whether they be fossil or not, but they do seem to understand geochemistry. And the principle here is that as an air parcel rises against a mountain slope, it's absorbed moisture from the ocean, wet air passes up over a mountain slope, and as it does, rain precipitates out. And the general principle is that heavy isotopes will tend to condense out of the air parcel more readily than the lighter isotopes. So as our air parcel rises up the mountain slope, it gets progressively depleted in the heavy isotopes. And as the parcel moves over the mountain slope, that parcel is isotopically light compared to when it began. And this fractionation process follows a Rayleigh distillation process, and it's very predictable in this simple situation. But before we kind of unpack that, what I'm going to do is just focus on two other uses of isotopes that are mentioned in this diagram from Deng and Jia in 2018. And one is, you may not be able to read it, carbon isotopes in the form of C13, and also deuterium isotopes, which are both involved in this process, but somewhat differently. So I've mentioned that this general process of Rayleigh distillation occurs. It applies to deuterium and oxygen, both water elements. And the one thing that we have to bear in mind with all isotope techniques is that the isotope fractionation has to be captured in what I'm calling a carrier material. Now that typically might be a mineral or organic matter, and this isotopic signal has to be preserved diagenically unaltered through time, along with similar contemporaneous data from the location at the start of the air parcel trajectory. So we have to have reliable measurements of isotopes at the start of the rise of the air parcel, as well as capturing the fractionation up the slope and preserving that unaltered through time in order for this technique to be reliable. Okay, carbon isotopes as a function of elevation. This is a technique which is only just being explored, it has to be said, although the idea has been around for a decade or more, possibly even more than that, maybe 2 decades. And the idea here is that photosynthesis will fractionate carbon isotopes differently depending on the mass of that carbon isotope. And because it's a function of photosynthesis, it is also a function of temperature, hence using it in a paleoelevation context, but also the partial pressure of oxygen, because oxygen competes for rubisco in the photosynthetic process. Observations in the modern world here show that for Ocotea lauraceae, there is a reasonably good relationship with delta 13C in alkanes, leaf waxes basically, and the red dots represent means, the grey dot represent the actual observations. Now you see there's a lot of scatter in this, but nevertheless it is possible to draw a reasonably good line showing there is that carbon isotope fractionation is a function of elevation. That's within one genus. We can extend that to different families and so on, but their families have different slopes. So what this means is that you have to be able to identify your plant material, and that plant material has to be present over considerable lengths of time, preferably at the genus level, time long enough for there to be changes in elevation on tectonic timescales. So you have to use plants that have, or plant genera that have a very long lifetime, tens of millions of years, in order to be able to be useful in paleoaltimetry in tectonics. There are also problems in as much as this is fundamentally relying on thermal lapse rates, and these thermal lapse rates used in this diagram will be ones which are based on dry bulb temperatures. So all I've said relating to dry versus wet bulb temperatures applies in this method. Deuterium in water is can also be used as an indicator of precipitation specifically. And here's an example of a technique being used in the Cascades in North America. And these authors argued that changes in the rain shadow effect that you get in terms of precipitation as a mountain range rises will give you some idea of when that mountain uplift occurred. This is all very well again, but if you look down here, the Cascade gymnosperms in dark green have a very different regression line to global gymnosperms. So this indicates the method is spatially very variable if you are just looking at the deuterium composition within, again, leaf wax alkanes. A better method seems to be using it in leaf wax is preserved in soils, because this gives you a more average result, even though the scatter is very high. But again, this is not an absolute or quantitative paleoaltimetric method. This just tells you when a rain shadow was developed. The way that we tend to use oxygen and hydrogen isotopes in paleoaltimetry tends to follow this fractionation, this Rayleigh fractionation relationship, which works extremely well on the windward side of a mountain. But as I hinted at earlier, as this air parcel goes over the mountain ridge, there is no way that you can recharge the heavy isotopes. So any moisture ending up on the leeward side will reflect isotopic fractionation that took place all the way up the windward side, and ultimately the height of the mountain range itself, not where the actual water was falling, let's say in a lake, in a basin. The result of that is that if you have a two-mountain system, and in particular in a monsoon situation where you have seasonal reversals of airflow, let's say here we go upslope, we lose our heavy isotopes and our air parcel produces moisture, let's say rain out on the leeward side of the mountain range or from up here. The moisture forming the lake in the intermontane basin is going to be reflective of both this elevation and, in the opposite season, this elevation when the rain is coming from a different direction. As a consequence, in this intermontane basin, all the isotopes in here are going to reflect the mountain ridge heights, and you will get a phantom plateau. So if you're in central Tibet, for example, you will appear to have a plateau even when you didn't, simply because these are all going to be light isotopes that are fractionated either at the mountain ridges or what normally happens at some height above the mountain ridges where the clouds form and the rain falls out. So when we test this in a modeling scenario situation, here we'll focus on scenario 2 again, where we've got our valley. This valley is not evident at all in the isotope signatures that you get. All you get is a phantom plateau. Even when you bias this towards the wet season, again, look at scenario 2, there is no valley there. And this is the ideal situation where you're biasing everything to when you get the maximum rainfall, wherever that time is in the year. The other problem is that you need to know the wind trajectories in your past landscapes in order to know where your source isotope was, or your source isotopic composition. Now, this isotopic composition varies within oceans, depending on ocean circulation, evaporation, salinity, all kinds of things. And so if you don't know the trajectory along which your air parcel traveled, you cannot reliably identify the source and therefore work out how high you are above sea level. So here I've got, this is an example from the Cretaceous, a very high resolution, 50-kilometer spatial resolution, all for the northern summer. And this is a GTEC paleogeography versus a Scottese paleogeography versus a Robertson's paleogeography. Put those into a climate model and you get very different wind trajectories, which I've emphasized here so you can see them in red. So, different paleoaltimetric techniques. Can we search for consilience? Well, consilience is something that people have recognized in the past, And it caused Ingalls et al. In 2020 to suggest we propose multi-proxy intrinsically cross-disciplinary studies to resolve inconsistent interpretations from otherwise unrelated proxies. In other words, they're asking for consilience. So let's just take Ingalls at their word and see how their consilience argument works for the Tibetan region. Now, Ingalls et al. Use clumped isotopes, and clumped isotopes are where you get isotopologues of carbon and oxygen forming slightly different molecular weight carbonates, and the degree to which you get different isotopes forming the carbonate is highly temperature dependent. Now, I'm not going to go into all the chemistry here. It's very complicated and it is being questioned, but just for the moment, let's take at face value the numbers in Ingalls et al.'s paper. So here we've got a clumped isotope temperature of 45 degrees C, and this temperature assumes a summer temperature. Carbonate formation is biased towards the warm season in their opinion, but at 0.5 meters below the soil surface. And they also assumed modern monsoon dynamics in their calculations. They also used the Rayleigh fractionation to derive an elevation of 4.4 kilometers for this area, which is in central Tibet. Okay, so they're arguing for a summer temperature in central Tibet of 45 degrees C, and this is for the Middle Eocene, and an elevation of that surface of 4.4 kilometers. Okay, what then does this result imply for sea level temperatures? Well, what we can do is we can use a climate model using their topography and derive from that a in this case dry bulb annual terrestrial thermal lapse rate for the summer, because we're looking at summer temperatures, and that is 3.76 degrees C per kilometer. If we apply that and assume their elevation is correct, then the summer temperature a half meter down in the soil at sea level is going to be 62 degrees C. Now, the problem with this is that once you go above 40 degrees C, the enzymes that carry out photosynthesis in vascular plants become denatured and lose functionality. So the photosynthetic rate declines extremely rapidly. To argue that ancient chemistry of photosynthesis was different from the present is untenable. Otherwise, this will be such a superb photosynthetic system, highly resistant to temperatures in temperature, that we would have it everywhere, and we don't. So there is something fundamental about the chemistry, the geometry of the isotopes in photosynthesis that get denatured once you go much above 40 degrees Celsius. They start to lose efficiency, and by 62, you would not have much in the way of Middle Eocene vegetation at sea level in the tropics, and we know that's nonsense because there's lots of plant fossils. Let's move on now to another case of consilience or lack of consilience. Now we're going to move to the Upper Eocene here. This is the upper nubile sediments in the Lumpula Basin of central Tibet. Ingalls et al. Get a clumped isotope temperature of 33 degrees C. Again, they're arguing for this to being quite high, and this is a temperature half a meter below the soil surface, right? 33 degrees C. Earlier this year, a paper was published in Geology by Shah et al., where they argue something completely different, They argue that there are conglomerates in a particular section, the Zhongmai section in the Lompola Basin, that can be interpreted as diamictites. Diamictites being a particular kind of conglomerate that is produced by glacial activity. This summer, we went to this locality because it was intriguing on a number of counts. Jia et al. Interpret certain features on bedding planes as being frost marks, and they certainly do look like ice crystal growth. And they also reported very small glendenite pseudomorphs after ichthyote. Now, ichthyote is generally thought to form in glacial or very low temperature environments. But in 2022, there was a paper published by Vickers et al., and they have observed it forming in nature at temperatures up to +7 degrees C. So even if this is a pseudomorph after ichthyote, and it's not convincing, it's very, very small, a millimeter or so across, and this could form easily overnight, even if you had a light frost. So it is not by itself an indicator of glacial conditions. Within the laminated marls that we have bearing these apparent ice signatures, frost marks, there are also thick organic layers, and there are rooting structures, etc., which all seems to indicate that there is lots of vegetation. Okay, so we've got this contrast between a summer temperature of +33 and an argument that we've got glaciation, and that because they have glaciation in this area in central Tibet, that central Tibetan plateau must have been very high in the Eocene, a globally warm period. Okay. However, what Xia et al. Ignored is that just above their dated horizon, this is a, I think the UPB date of 35, so we know the age. This volcanic ash occurs in the marl succession bearing the frost marks and the glendonites. 10 meters above this dated horizon, which you can easily find in the field, there is a fossil flora, and this fossil flora has been interpreted as being subtropical. It contains legumes such as podocarpium, paper published by Li et al. In 2022, and in general, the overall flora looks very similar to one that in the nearby Dayu flora. Dayu flora is 38 million years, so slightly older than the 35 that we have here. But the flora in the Zhongmai section here is very similar to the Dayu flora. And the Dayu flora has palms in it. And when we do a clamp analysis, we get a cold month mean temperature of below 7.2, which is entirely consistent with periodic frosts, even though we have palms. Palms can tolerate frost, providing they're not deep and prolonged. And clamp analysis suggests an elevation of 2.6 kilometers, not something extremely high, i.e. above 4 to 5 kilometers. So in their geology paper, ignoring the fact that there is a plant bed containing palms, etc., within the same section as their frost marks, they come to the conclusion that it was glacial and high, whereas contradictory, non-consilient evidence within the same section suggests that it was warm and low. Now, I mentioned clumped isotopes and the fact that people often assume that the carbonates form in the warmest part of the year, the summer. Unfortunately, it's not as simple as that. Carbonates can only form when the soil is drying, so rainfall is also important, soil moisture is important. And here, what we did in a paper in 2002 is run a climate model for various valley versus plateau scenarios for central Tibet, and to see what the changes in rainfall and soil moisture were. And you can see here, this is the soil moisture at, I think this is between 20 to 65 centimeters in the soil, roughly equivalent to the Ingalls half meter down carbonate formation. And you can see the soil dries throughout the summer, which is fine, but also it's very wet to begin with in April. When we look at precipitation evaporation on the surface, we get this pattern. And when we combine everything together, we can identify multiple periods within the year when you might get the carbonate forming. And here are the main, in these red boxes, these are the periods when carbonate is most likely to form in these situations. This is precipitation here now. And this shows that the temperatures you get are not necessarily the summer temperatures. They represent something in between, closer perhaps to the mean annual, but not necessarily the summer. And basically, without going into a lot of detail, what we found using this approach is that there are basically two scenarios that fit the available clumped isotope and other data. One is at 45 million years, you have an elevation of 1.7 plus or minus 0.9 kilometers for central Tibet. But at 30 million years, you will have risen to around 4 kilometers. And those are the only situations that fit all the available data where you have consilience. Moving to Eastern Tibet just quickly, using a consilient approach, what we've been able to show is that Eastern Tibet rose from a low landscape, desert landscape at around 50 million years to, by the time we're in between 40 and 30 million years, the present landscape had been achieved. And this is true whether you're using isotopes or fossils, it doesn't matter. They're all telling you roughly the same result. If we extend that approach across the whole of the pan-Tibetan region, this is the most up-to-date scenario that we can come up for the building of the Tibetan plateau. Back here at 100 million years ago, central Tibet is roughly at sea level, but we are beginning to build two mountain systems. The Changtang is indotted because we really don't have a lot of quantitative paleoaltimetry to constrain it. This is just based on tectonics, and so it's dotted. But the Gangdesi, we can track the rise of the Gangdesi from 100 million years ago when it was near sea level, right the way through to the present using isotopes. And there is a consistent rise, forming the modern elevation soon after 60 million years ago. Now, because we've got two mountain systems, within them we have a valley, and here you can see the elevation of that valley. The valley is shown in the green sort of outline here. At around 61 to 65 million years ago, we have the onset of the India-Asia collision, and then subsequently India slows down as it meets more and more resistance in the form of Asia. So we can bring all these together. And soon after the onset of the collision, we get deformation of the rocks across the wide central valley, and we begin to elevate that central valley. The first part to go up is Eastern Tibet. That gets squeezed out sideways. And you've seen the results I've just shown you for Eastern Tibet. So we build Eastern Tibet such that by 40 million years, it's already high. That leaves a closed off central valley which is open to the west and drainage to the west. But soon after 40 million, we begin to rise the elevation of central Tibet, going up through 2 kilometers to 3 kilometers to 4 kilometers and so on. The last area to rise in the Tibetan Plateau is northern Tibet, although there are big uncertainties about this. We may be going back later in the summer of 2024 to try and look at northern Tibet. And the last piece of real estate in the Pan-Tibetan region are the Himalaya, which really only grow between 23 and 15 million. By 15 million, they're more or less at 5 kilometers, and subsequently the peaks have continued to grow. So to summarize the formation of Tibet back in the Cretaceous, we know that there are marine sediments in central Tibet, so it must be by definition at sea level. By the Middle Eocene, we are around 2 kilometers elevation. By the Miocene, Middle Miocene, we're roughly at the present elevation. And when we build the Himalaya, that forms a rain shadow, and the wooded landscape that we have in the Middle Miocene disappears and becomes the modern alpine steppe. Sediment provenance studies that have been done recently are also supporting this general model of Tibetan growth. So, last two slides. This summarizes what I think is perhaps the best way of going about looking at surface height, given that no single discipline or proxy provides a standalone paleoaltimetric magic bullet. So what we have to do is use an iterative approach to achieve consilience. So let's suppose we start off by getting some leaf fossils, and we can derive moist enthalpy from those using CLAMP. Moist enthalpy gives you the most resilient elevational elevation estimate, because you don't have to know air partial trajectories or anything like that. And once the air particle goes over the ridge, you recharge the moist enthalpy, unlike the isotopes, which are a one-shot only deal. So this is the most robust technique. But allow you to come up with a first order topography that you can put into climate modeling. You can then derive wind trajectories and use isotopic fractionation if you've got an isotope fractionation component within your model. That suggests where you might go for future field campaigns. You collect isotopically derived material to get surface heights from those. They can then go into improving your climate model, resolution or process based, more field campaigns. And so you keep going around this circle of iteration to gradually improve your knowledge of the past landscapes. Thank you very much.
Thank you, Bob, for your brilliant talk, but difficult to understand everything.
Well, you can watch it again on YouTube.
Yeah, I will do it. Now it's
there is a lot in there, and it goes outside of paleobotanical comfort zones. I realize that, but understanding surface height is really important, because let's suppose we want to measure temperatures using plant fossils across Asia, such as in neckline, for example. Unless you know the height at which your fossils were being deposited in the Neogene, in the case of neckline, you cannot legitimately compare one place with another and interpret those in terms of climate systems.
What I didn't understand, that perhaps it's a very simple thing, but you told that it is important to know the direction of the wind. But yes, how you can know it for the past?
Yeah, this is where it's very important to get your paleogeography correct, and in particular have some idea, at least a first order idea, of what elevations are. You don't need to know wind directions for moist enthalpy approach, because as I showed in an earlier slide, let me go back to that slide. This one, I think, is. Yeah. This is just simply moist enthalpy differences, and it doesn't matter what your wind direction is. Moist enthalpy can still reconstruct the past topography. This is in a model context. In reality, of course, the data density that we have from fossil leaves isn't that great. So what we need to do is to get some idea, put it into our model, use the model, a climate model, to predict wind trajectories. And once you know the wind trajectories, you know where to go into the field to look for proxy data that will give you isotopic information. You compare those with your model results, and you can improve your surface heights that way, and so on. But you have to use climate modeling to understand your wind patterns, and you have to use climate modeling to interpret your clumped isotope data. So modeling is absolutely essential to use alongside the proxies, and you can't use one without the other, in my view.
Mm-hmm. Thank you. It became a bit more understandable. Well, and now it's time for a question. And if anybody wants to pose a question, just switch on your phone and raise your hand, and I'll let you to speak. Well, or otherwise you may write in the chat, and Bob will read your question in the chat. Well, so far
everybody's gone to sleep, or they are watching.
Impressed too much.
What? Sorry?
Well, indeed, no questions. Well, in the chat, look.
Yeah, there is a little question.
Yeah.
Great seeing you too. Well, except I can't, but at the moment, but never mind. Are we assuming the isotopic signature is all rain out? Very good question. Generally speaking, in isotopic fractionation, you are assuming that the rain out is the dominant signature. So let me go back to this one. Actually, this one would be the best one. But it's complicated because it depends on which isotope system you're using, and it depends what carrier you're using. So if you're using deuterium in leaf waxes, for example, a lot of that is also determined by evaporation as well as rainout. If you're dealing with either deuterium or oxygen, you may not be directly sampling rainout at that point, but your soil moisture will be containing, or the soils will be containing moisture which is flowing downslope within the soil system. And also it may be downslope, your carbonates in lakes, for example, will be containing moisture which may be averaged over long periods of time because it comes from snowpack. And the fractionation process for snow is slightly different to that for rain. So there are a number of different complicating factors that have to be included. And for the sake of simplicity, I didn't go into those. But they are all, to some extent, included in most isotope paleoaltimetry. but it has to be said that a lot of the time these are assumptions. And so people are assuming air partial trajectories. Ingalls et al., for example, assumed the modern monsoon system for the Middle Eocene. We now know that in the Middle Eocene, largely because of work we have done on Eastern Tibet, this one, that once you build Eastern Tibet, that changes the atmospheric circulation over the region that I've got in the yellow circle here. And what this leads to is an increase in overall rainfall, but it is not the modern monsoon. The rain falls both in the spring and in the autumn, and you have a relatively dry summer and a relatively dry winter. Now, a relatively dry summer is not a modern monsoon because the Asian monsoon is summer wet. So as you build the topography, you change atmospheric dynamics and you change the precipitation pattern. So to assume anywhere in the Tibetan region that you have in the Eocene a modern monsoon is false. It's a false assumption. And similarly, the other assumptions that you build into isotope geochemistry, if you don't test them with climate models, can be false.
Thank you. A question from Ben Lepage in the chat. What about groundwater and or transpiration?
The groundwater can be tens of thousands of years old, and it also takes tens of thousands of years for soils to develop nodules. So you're really looking at average conditions over very long periods of time. Compare that to leaves, and here you will know that I am highly biased in favor of leaves. Leaves can vary their morphology on a season by season basis. And we can demonstrate that by having a closed canopy forest. You cut down a tree and the leaves produced the following year by the adjacent trees are different to the ones which were produced previously in the understory because they now have more light and the moisture regime has changed, the humidity has changed. So I absolutely agree with you that there are different timescales involved in using these different paleoaltimetric techniques.
Mm-hmm. So you perhaps answers to the comments that Ben just have written. Look.
Yeah. Yeah. And it not matters geologically, but groundwater, yes. And also the groundwater process itself, you get, it depends again which isotope system you're using, but soils tend to undergo a variety of different chemical alterations over time. You get respiration of bacteria and blah, blah, blah in the soil. And it's a very complex system. But as I showed earlier with the rain shadow effect, the soils generally tend to give you a more consistent outcome than using leaf wax information on individual groups of fossils or individual fossils, because there we can see that the slopes of the regressions vary between the cascades and the global, whereas the cascade soils are very similar to global soils. It's highly complicated, and what you have to be when you're doing any kind of paleoaltimetry and looking for consilience, you have to understand the assumptions, the strengths and the weaknesses in every method that you're trying to compare in order to make some sense. Unfortunately, we have a lot of articles in the literature that have only looked at their, authors have only looked at their particular technique, and they've thrown a number out in the results without any consideration of how that number compares to other numbers derived from other techniques applying to the same area. And this is why in Tibet we've got this huge dichotomy between the people arguing for a high plateau in the Eocene and a low valley in the Eocene.
We skipped temporarily one more question from Tatiana Faraponova. Look in chat. Could you please repeat what are the cascades gymnosperms? It's from the slide about deuterium as indicator of precipitation.
Sorry, just a minute.
Look.
I'm looking at a different one.
Perhaps it's...
I'm looking at Eugenie.
If you prefer, the last
can I go with this one, and then you can repeat your question in a minute?
Okay, yeah, but read the question as well.
Yeah. Do you know about database 5 glendenite in Phanerozoic, which I'm not familiar with that, but it would certainly be worth you sending me the details on that. Back in the 1970s, I went looking for glendonites, well, ichhyite pseudomorphs, glendenite pseudomorphs after ichhyite in the Arctic Ocean. I took off my field trousers and shirt and waded into the Arctic Ocean amongst ice floes with just a t-shirt on, feeling for glendonites with my toes, because they were very large crystals that I could feel. I could only feel them for about 2 minutes before my toes went numb, but I did recover a number of good fist-sized glendonites. Mm-hmm. And back then we were assuming that glendonites would only form in sub-zero temperatures, preferably at high pressure with high organic content. And more recent work has shown that that is not necessarily the true, and that ichhyite is stable for a few hours, but not more than that, at temperatures up to +7, provided that you've also got a lot of magnesium in the system. But the kind of glendonite pseudomorphs that were being reported from central Tibet, as I said, are very small, are ambiguous, and could easily have formed in mildly chilled temperatures, particularly as these are marls with reasonably good magnesium in there. So I'm not convinced that this indicates very cold temperatures for a very long time. So what was the other question? Sorry.
About cascade gymnosperms. What are they?
There's cuprous E and there's pinase E, and the cuprous E have a different, and I haven't got this in the presentation, but the cuprous E and pinase E have got, again, very different slopes to their regressions. And it's thought that this is a function of the way they handle water, with the pines and the cupressus having rather different water management strategies. If you read the paper, Sisley et al. 2023, you will see what I mean by that.
Mm-hmm. Thank you. And some more thanks in the chat from Svetlana Polevova. Thanks from Tatiana.
Thank you as well.
Yeah. And any voice question? Wow. You may switch on the microphone.
Ben, are you wanting to ask a question? Just waving. Okay.
Okay.
Okay. Bye.
Well, if you if we do not have any more questions, so we can say once again, thank you very much for your interesting presentation. Thank you for coming.
Thank you very much.
Is that
now we can see some faces.
Report.
Right, yeah. Let's see who's out there. Yeah, I can see Natasha. Yeah, yeah. Okay, I got several pages here to go through. Han, I can see Han. Hi. Anyway, thank you for inviting me to give this talk. It didn't include nice movies of dinosaurs this time. Apologies. But this is something which has been intriguing me after our umbrella project, and so I will actually Howard Falcon Lang has invited me to write this up for P3 at some point, so in due course you may see a paper with more detail.
Thank you, Bob. Thank you, everybody, and bye.
Bye-bye. Bye-bye.